All right, so we're going to start it off with Sean. Elka, if you'd like to make a quick introduction for Sean.
Thank you very much. Sean Phillips is going to be presenting the first presentation. He worked in the Storm group. He worked with me, Storm Shear Turbulence Research from Mesocosm. And he's going to talk about Storm. It's a series of two students presenting from this summer's research. And Sean Phillips worked on it, and Rihanna Shalters, who's coming next after this. So Sean Phillips is going to talk about mimicking storms in experimental ecosystems and stepwise erosion experiments. Sean, you can come here.
Hello, my name is Sean Phillips. I'm mimicking my name is Sean Phillips. My mentor was Dr. Elka Portal. I'm mimicking storms in a experimental setting and see what the effects of resuspension are in an experimental ecosystem. Objectives: determine the effects of biodeposit export on ecosystem processes. Determine the critical shield stress. Determine how that shear stress might affect biodeposit quality and quantity in cistern and TSS, which is total spin solids. And so I'm focusing on mimicking storm in a setting, and my colleague Liana is focusing on ecosystem processes. Research method: mesocosm experiment. Our mesocosm experiments are large ecosystem experiments. And also we focus also something to do with morning measurement, which we use several different devices to measure the different data points throughout the days of the experiment. And my colleague Liana, we're focusing on that. Also, we did 2 storm experiments over the course of the experiment. There were 2 storm days, which were long, they would get a lot of data. We also had storm, as I said before, we had storm days. And finally, also had OBS calibration. And we had to do this in the end of the experiment. OBS stands for optical backscatter. And we had OBS calibration and they measure turbidity. Storm experiment. This is a timeline of the experiment. First, we had to collect soil data from the experiment. We had to collect soil from the riverbed. And the first time we tried this, we accidentally lost one. We actually lost the thing that used to gather the soil sediment with. And after that, we had all the soil sediment set out for a few days, so we kill any organisms in the sediment to not affect the results. And then we also let it stay out for a few more days, so it will not affect. So we're going to moon area out and release ammonia. Then we had 2 storms, 1 day, 1 week apart. And then at the end of this thing, we had a flex experiment, which was done at Horn Point Laboratory. Here's a chart describing some of the soil-based nitrogen cycle and shear stress. Shear stress is the friction caused by sediment and water in an ecosystem, and critical shear stress is when that sediment is resuspended in the water column. Mixing. This is so a picture. The first one up above is the mixing system. That's below, actually, sorry. This is the mixing system, which is, you see the several instruments help control the data, instruments and control the data and collect the data. And there's also a battery backup too. So if we lost power, these are the tanks. So above are the tanks, which would be filled up with water, and we use the experiment to collect data. And over there is a stone paddle, which was used to mix the sediment during the whole experiment. And here the oysters we used for biodeposit from during the course of the experiment. And this is OBS. As you can see, the log is darker as the shear stress increases. And OBS calibration was done at the end of the experiment. So we have sediment and biodeposit in the water so we can collect good data. And I use a polynomial fit can analyze the data for all tanks 1 through 6. And these are examples of 4 and 5. And these are graphs from some of the storms. This is from storm 5, 1 and 2. I mean, sorry, tank 5, 1 and 2. Yeah, sorry. And these graphs determine the TSS in the water column and the amount and see how much is resuspended. And as you can see, it goes up by steps until it gets to 0.6. And we had 0.3. 0.3 when the amount was starting to be resuspended in the water column. And we had export and non-export tanks. Export meant that the tank that matter was not allowed to settle out after the storm ended. And with non-export tanks, matter was allowed to settle out before the tanks were drained by 50%. Again, as you can see, it steps up, and also 0.3 when stuff was starting to be resuspended in the water column. And as you see, the data is higher for storm 2 than storm 1. And these are taken during one of the storms. Particular organic matter and particular organic inorganic matter was decreased as the storm went up. And we measured it 0, 0.45, and 0.6. And at the same time, TSF, which stands for total suspended solids, increased throughout the storm. And we get into something else, and this is particular organic matter, which increased during the experiment. And for both graphs, we did not take measurements at 0.3 because they're not suspended matter in the wall column to give good data at that point. So that's why we didn't do that. And this also may affect water quality and decrease oxygen in the water column. And these are some of the research findings. This is the first time a storm in a storm environment. Resuspended TSS from storms would vary between 1 and 2. And the TSS stands for total suspended solids. And it might be an effect because between storm 1, meaning the salt, and storm 1 is about a 4-week period where there's no resuspension. Between 1 and 2, there's only about a 1-week period with no resuspension that might affect our results. The critical shield shift was 0.3. System quality, palm and pin, which is particular organic inorganic matter, decreased with resuspension, and palm increased with resuspension. Conclusions: mimicking storm experiment setting, the length of time when resuspension did not affect the amount of TSS. System quality decreased with resuspension, palm increased with resuspension, and with the first of its kind research. And special thanks to everybody who helped us out on the day we added mud to the tank. And the reason why me and Miana was so dirty is because we actually got into the tanks. And the way we got in the tanks is we put a big ladder next to the tank, put a small ladder in the tank, climbed in. Then the people helping us out, they handed us buckets to jump into the tanks. And then we had to walk on like you do if you're swishing like grapes or wine. Even out the mud, so it was so dirty. And also extra special thanks to John, who helped with various aspects of the experiment, technical and non-technical. And also special thanks to Mike and Jeff from Hornpoint, who helped us collect various aspects of data. And also a special thanks to Maryland Sea Grant for funding the experiment. Questions?
Are there any surprising findings? Anything that you discovered throughout the the 10-week internship that really kind of just jumped out at you? Something that you and your team did not expect or anticipate?
Yeah, I think Elka was surprised by the initial results. She expected something differently at first, but we got results that we did not expect from our experiments.